The recommended maximum load for a 110 volts AC circuit is 60% of the circuit capacity. For a 208 to 250 volts AC circuit, the recommended maximum load is 80% of the circuit capacity. Now let's consider a specific example. The maximum ampacity for a 20 amp circuit is, of course, 20 amps. However, adhering to the recommended maximum load of 60%, the practical maximum load on that 20 amp circuit should be 12 amps. The primary reason for these recommended maximum load percentages is the phenomenon of power inrush, also known as inrush current. When numerous devices are energized concurrently, they exhibit a tendency to draw a substantial surge of current over a brief duration. This inrush current can considerably surpass the steady-state current draw. This phenomenon can potentially lead to the tripping of circuit breakers or inflict damage upon equipment if the circuit is subjected to overloading. To find more information on this topic, you can consult several industry standards and building codes, including firstly, the National Electrical Code, or NEC, secondly, the Institute of Electrical and Electronics Engineers Standard 3007, and thirdly, the American Society of Heating, Refrigerating and Air Conditioning Engineers Handbook, also known as ASHRAE. Let's delve into inrush current a bit more deeply. Inrush current is the instantaneous high input current drawn by an electrical device when it is first turned on. Capacitive loads, inductive loads, and motors are the most common causes of inrush current. Inrush current can be many times larger than the normal steady-state current of the device and can last for a few milliseconds to a few seconds. In data centers, where multiple devices are often powered on simultaneously, the cumulative inrush current can be significant. If the circuit is not properly sized to handle this inrush current, it can lead to nuisance tripping of circuit breakers, voltage dips, and equipment damage. To mitigate the effects of inrush current, several strategies can be employed. Firstly, sequential power-up. Staggering the power-up sequence of devices can reduce the overall inrush current at any given time. This can be achieved through intelligent power distribution units, also known as PDU, or through software-controlled power management systems. Secondly, current-limiting devices. Devices such as soft starters, inrush current limiters, and solid-state relays can be used to limit the inrush current drawn by individual devices. These devices gradually increase the voltage applied to the load, reducing the initial current surge. Thirdly, appropriately sized circuit breakers and wiring. Ensuring that the circuit breakers and wiring are adequately sized to handle the anticipated inrush current is crucial. This involves calculating the total inrush current based on the devices connected to the circuit and selecting circuit breakers and wiring with sufficient ampacity and interrupting capacity. Now let's discuss the National Electrical Code, or NEC, which provides comprehensive guidelines for electrical installations in buildings. The NEC addresses various aspects of electrical safety, including overcurrent protection, conductor sizing, and equipment grounding. Several articles within the NEC are relevant to determining the appropriate maximum load for circuits. NEC Article 210.20, Overcurrent Protection, specifies the requirements for overcurrent protection devices, such as circuit breakers and fuses. It mandates that the overcurrent protection device must be rated to protect the circuit conductors and equipment connected to the circuit. NEC Article 220, Branch Circuit, feeder, and service calculations, provides detailed instructions for calculating the load on branch circuits, feeders, and service conductors. It includes factors for various types of loads such as lighting, receptacles, and motor loads. NEC Table 310.15b16, allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees C through 90 degrees C, not more than 3 current carrying conductors in raceway or cable or earth, based on ambient temperature of 30 degrees C, provides the allowable ampacities for different sizes of conductors based on their insulation type and ambient temperature. It is essential to consult this table to ensure that the conductors are adequately sized for the anticipated load. NEC Article 645, Information Technology Equipment, provides specific requirements for electrical installations in information technology equipment rooms, including data centers. It addresses issues such as grounding, bonding, and overcurrent protection for sensitive electronic equipment. Let's also discuss IEEE Standard 3007, recommended practice for the design of electrical systems for industrial and commercial power systems. This standard provides guidance on the design of electrical systems for industrial and commercial facilities, including data centers. It covers topics such as load calculations, power distribution, grounding, and power quality. IEEE Standard 3007 recommends dating circuit breakers and conductors to account for harmonic currents, voltage distortion, and other factors that can affect the performance of electrical equipment. It also provides guidance on selecting appropriate overcurrent protection devices to protect against both overload and short-circuit conditions. And let's discuss ASHRAE, which provides guidelines for heating, ventilating, and air conditioning systems in buildings. Although ASHRAE primarily focuses on HVAC systems, it also addresses electrical aspects related to these systems, such as motor loads, control systems, and power quality. The ASHRAE handbook includes information on calculating the electrical load imposed by HVAC equipment and selecting appropriate wiring and overcurrent protection devices. It also provides guidance on energy-efficient design practices that can help reduce the overall electrical load in buildings. So, to reiterate, understanding and adhering to the recommended maximum load guidelines for electrical circuits is crucial for ensuring the safety and reliability of electrical systems, especially in data centers where sensitive electronic equipment is prevalent. By considering factors such as inrush current, conductor sizing, and overcurrent protection, and by consulting relevant industry standards and built-in codes, it is possible to design and operate electrical systems that can handle the demands of modern technology while minimizing the risk of electrical hazards. Firstly, ensure that you consult the latest edition of the National Electrical Code, or NEC, for the most up-to-date requirements and recommendations for electrical installations. Secondly, consider consulting with a qualified electrical engineer to perform load calculations and design the electrical system to meet the specific needs of the facility. Thirdly, implement a robust power management system that monitors circuit loads and provides alerts when circuits approach their maximum capacity. Fourthly, regularly inspect and maintain electrical equipment to identify and address potential problems before they lead to failures. Lastly, provide training to personnel on safe electrical practices and procedures to ensure that they are aware of the risks associated with electrical hazards. Always remember that electrical work should only be performed by qualified and licensed electricians who are familiar with the applicable codes and standards.